Alright, so this is some epic amaze biz, and forgive my janky, disorganized setup, but I am super stoked about this. So I have this really cool, like, starlight LED light thing that is pretty snazzy, changes colors, does all kinds of cool stuff. And I'm, like, sort of doing some upgrades to it right now. Mostly to learn. You know, they do make more expensive ones, but this one was cheap. But I'm learning, and it's cool. It's fun hacking stuff. One of the things, though, I really don't like about this, and a lot of modern electronics, is you have touch-sensitive controls. So you actually power this on through a touch sensor. By the way, notice there's a curved bezel on this, which makes it additionally harder to get it to sense anything. And then it also does the same for volume left and right, and for next track and previous track. I don't really care about the speaker Bluetooth music options for this because I am not using it for that. It's a crappy speaker. But what I do like is the lights, and they actually rotate and stuff too. And so what I'm doing right now is what I've been wanting to do is get this power button to be a clicky button instead of this touch sensitive deal. Well, you might think that's pretty easy. It's actually not. So first off, you have a microcontroller that's converting all the touch sensitive stuff into pulses, which it sends to a secondary microcontroller, which is on this main large green board here, which is powered through 5 volts. So there's this cable here. I actually replaced the original cable with a better quality one. The original one was janky. I don't like these cables. I mean, good enough for the manufacturing, but can't even tell what wire by color. So anyway, I put a nicer cable loom on here so I could actually check things out. And I'm going to show you what I did. This is really cool. So this microcontroller, by the way, the part number is sanded off, so I don't even know what part it is. But even if I did, I wouldn't have the code to program it. So what I've done, this is so cool, is I've programmed an Arduino Nano microcontroller to mimic the code that is being spit out of this mystery microcontroller. It mimics that code, sends it to the main CPU, and turns it on with a push button, a clicky push button, which I have down here, instead of the annoying touch-sensitive control, which is under this large, I've had to you can't see at night. I mean, the whole point is you want to use this thing when it's dark, and it's nice to be able to feel tactile controls when it's dark. And so as you can see now, I can change all the light modes and turn it off with this push button. I don't have to mess with that touch-sensitive control anymore. This is really cool. It's something I've been wanting to do for a while. I'm super excited about it. So let me show you how that's done. I have my oscilloscope over here and all my probes on everything. And first I'm going to show you what happens when I put my finger on the touch sensor. And the scope, there's two probes hooked up, and so the top one will show you that's the waveform it gives. Now, if we go to a trigger pulse, so in this case, I'll do trigger on the 2, which is what I'm showing you right now. It'll stop and give you an idea of what we're looking at. Well, what are we looking at? We're looking at a fairly low frequency pulse. As you can see, it says on the bottom there, it's about 67 hertz. It's the grid is set up to be in divisions of 10 milliseconds, and you'll see pretty much everything is there's a 5. So it starts off with a 5 millisecond low, then a 5 millisecond high, then what looks to be like a 2 millisecond low, 2 millisecond high, 2 millisecond low, 2 millisecond. It's a 5 millisecond high, 2 millisecond low, 2 millisecond high. Anyway, you can see it's got this pattern, right? And then it goes to a long 10 millisecond low, and then it's actually cut off, but there's a 10 millisecond high. So this pattern repeats every 100 milliseconds, and it's all 10, 5, and 2 millisecond waveforms. Okay, so it's not the easiest duty cycle to replicate, but we have an idea of what it is. Now, you can see when I click my button down here, and if I put it on a source so that the oscilloscope stops it when I click for the trigger, you'll see that it replicates it almost perfectly. I'm not sure why it's not stopping. Let me set down the phone for a second and see if I can get the oscilloscope to freeze frame. So I just have to press the stop button, which I couldn't do while I was holding my phone. And so you see here we have a very similar, nearly identical setup. The waveforms actually look a little bit cleaner, which is not too surprising. Who knows the quality of that microcontroller? But if we, unfortunately, let's see if I can get both to run at the same time. If I use my, if I'm quick with my hand, let's see. It's hard to do. Let me get my phone. Get a phone holder of sorts here. Rig something up. Okay, so now I'm going to run both at the same time and check that out. They're very, very similar. Now they're going to be slightly out of phase because there is like a, I think part of that has to do with if I'm hitting them at the same time. Yeah, there you go. So now you can see they're actually almost one-to-one aligned right now. There is a slight phase shift on the original pulse because I think it actually sends one additional pulse at some point, probably for the audio or track setting. I haven't analyzed it super closely over the course of hundreds of milliseconds. I just wanted to get it something like roughly in ballpark so that I knew I could turn it on. So if we look over on my computer here, the way the code is set up, I did this through what's called PWM bitbanging. And you can do this, I'm sure, with the analog write function. There's ways to do stuff. But what I ended up doing was, if you go down here, if the button for the MCU is low, then digital write a 10-second low pulse and a 10-second high pulse. Those are the first two large pulses. And then do all those short ones. 5, and then I actually wrote these out. 5, 2, I wrote out on paper originally. 5, 2, 5, 2, 2, you know, just all the way down. And all this is doing is turning the output off and on, off and on, off and on, off and on in the same pulses to mimic the pulses that microcontroller spits out. And this is called bit banging because you're not actually setting a PWM cycle with the analog write function. You're just digital write. You're just turning this pin off. You're waiting for 5 milliseconds, then you're turning it on. Then you're waiting for 5 milliseconds, you're turning it off. Waiting for 2 seconds, turning it on. 2 milliseconds. And that's all you're doing. That's how you're making those pulses. And if nothing's happening on that button, then you just keep it low. That's it. This will output a 5-volt tolerant signal because it's a 5-volt Arduino. So the very last step was I put a resistor voltage divider. And this isn't the best way for high-speed signals to do this, but because this is not a high-speed signal, a simple voltage divider will work and you don't actually need a level shifter. And that's it. But I'm excited, folks. This is pretty cool stuff. Now I don't have to mess with those touch controls. And this also means I can use this way of doing things for anything I find that is touch control. I know how to do this now, how to pull the PWM bitbang and mimic the pulse coming from the touch sensor controls. As long as it's not all totally integrated, I should be able to do this with other electronics as well. Long live the touch of tactile buttons. That's it for this. Have fun hacking, folks. This is Sega Sonic Fan, signing out.